Hey everyone, in this part of the video, we will talk about spatial data querying and filtering. So we can query or filter spatial data based on both attributes and geometric properties. So if we choose to filter spatial data based on attributes, it's very similar to how we query any pandas data frame using comparison or Boolean operator. So for example, in the Virginia census tract, we have census tracts for all across Virginia state. Say in this particular query, we want to filter the census tracts that is only located within Fairfax County. And here we can perform filtering by attributes, and we are saying that select or identify the census tracts where the county FIPS code is 059. That is the Fairfax County FIPS code. And you can see the output. It is only showing the census tract located within Fairfax County. Now, if we perform spatial filtering by location, we can select geometries based on their spatial relationship to geometries within another dataset. So we commonly use spatial filtering to extract features from one layer that meet specific spatial conditions relative to another layer. And to perform any spatial filtering, both datasets must be in the same coordinate reference system to ensure the accurate spatial comparison. And we can perform spatial filtering or spatial querying based on various binary predicates. For example, if we use this intersects function, we will identify geometries that share any portion of its space with another geometries. Then if we use this touches predicate, it will identify geometries that only touches another geometries. Then for with the within function, it will identify geometries that's fully inside another geometry. Then the contains, it will identify geometry that completely encloses another. There are also other binary predicates available for filtering. So you can go through this link to identify this, to see and learn about these predicates. Now, the output of spatial filtering will vary depending on the type of binary predicate we are using. So for example, if we want to select roads that's located within Fairfax County and a specific tract, say 461700, the output will vary depending on whether or not we are using an intersect option, within option, or contain option. And each method will return a different subset of data that we will see later in this example. So the first thing first, we need to check the CRS. Um, in this case, both of these dataset are coming from title line shapefile, so that's why their uh, CRS is same. And then, as I said, we want to extract the road for a specific tract. So first we are doing a filtering based on attributes, and we are identifying the tract specific to this FIPS code 461700. And here you can see the output. So a very important note here, when we perform spatial index filtering, the row index values of the filtered data remain the same as the original data set. So when we do filtering, it does not automatically reassign the new index value. For example, in this case, you can see that index value for this tract is 2048, and this index value was just like this in the original VA tract dataset. You can use the reset index method to change the indexing and put a sequential indexing value if you need to. But for this particular case, we didn't do that. So whenever we are calling any attributes for this particular tract from this data set, we need to use this index value 2048. Now, the first filtering here, we are subsetting the row data that intersects with the geometry of tract 461700. And see, we are first calling the road dataset, and then we are saying, okay, identify the road geometry that intersects with the track geometry, and inside we are putting the index 2048. And here the output is returning a subset of roads that either touches or overlap with the tract boundary. So here you can see the output. The green color is the tract boundary, entire tract area, and the red color are the roads we found after doing this filtering. Next, in this one, we are using this within function, and when we are using this within function, the filtering returns a subset of road that are completely inside the tract. So here you can see the output. So we are only identifying the roads that completely or absolutely falls within this tract. Then in the last one, we're using this touches predicate, and it's returning the subset of rows that only touches the polygon boundary of this tract. Now, so here we have another example in a different context. Say we want to identify which hospital locations actually falls within Fairfax County. And again, first we need to check the CRS for hospitals and Fairfax County. And you can see there's a discrepancy between these two data sets CRS. So we need to first convert it to the same CRS. We can use the toCRS function for that purpose. And once the conversion is done, we can double check and make sure they are converted to the same. And here, so the Fairfax County geodata frame has multiple polygon geometries, and each of them represent multiple tracks. And we can combine this multiple polygon geometries into a multi-polygon using the unary union. And this part is particularly necessary to perform the spatial filtering, because we can only perform spatial filtering using a single shapely geometry object. So if we try to filter using the entire geometry column, which is actually stored as a geoseries, the spatial filtering won't work. So first we need to apply the unary union. Then we can merge all the shapely polygon objects within the Fairfax County geometry column into a single multi-polygon. And then we can make it compatible for spatial queries. So here, first I'm creating this multi-polygon, and if you check the type of this newly created geometry, you can see that it is now a multi-polygon, and this is what the new geometry looks like. You see there's no individual track boundary inside. And next, we can perform spatial filtering with this multi-polygon, and we are identifying the hospitals that's located within this particular Fairfax County geom. And also we can print the shape of this data subset, and you can see that there are 48 rows in this filtered data, which tells us that there's 48 hospitals out of the 76 hospitals that are located within the Fairfax County boundaries. And you can also see the output hospital locations we got, and overlaid on top of the Fairfax County boundaries data. Now, another example is here. So in this case, we want to identify the name of the census tract within which the first hospital or the hospital locations at index 0 is located. So for this case, we can use the contains function for spatial filtering. So here you should particularly note the difference between contains and within function. So we use contains where we want to identify which polygon is containing a point, versus we use within a function when we want to identify which the points that is located within a polygon. So for this particular case, we want to identify which Fairfax County tract is containing the first hospital geometry at index position 0, and it's returning us this particular tract, tract 482203, that is containing the first hospital locations. And here you can also see the map. So this particular very tiny green polygon boundary, it's referring to this tract where the first hospital at index position 0 is located. So now spatial filtering only returns the data subset, but it do not merge the attributes or the columns from the both data frame. We can achieve this using spatial join. So in Python, we have this sjoin function under GeoPandas module that we can use. So within sjoin, we also need to define the binary predicate that we discussed for spatial filtering. On top of that, we also need to specify the join type. So if we specify left join, that means it keeps all rows from the left data frame. If we specify the right join, that means we are keeping all rows from the right data frame. And the inner join means we are only keeping the rows where the binary predicate is true in both data frame. And here you can see some other resources that you can follow to understand how spatial join works. In our example, so let's say we want to join the road data set with the tract 461700 boundary data. And again, for spatial join, both data set need to have the same CRS. So first, check the CRS, and if they are the same, in that case, we can join them. So here in this particular case, we are saying that, okay, join the road data using this sjoin function with the track data, and how? Using inner join, and the predicate would be intersect. So we will only join when the road data is intersecting with track data. And as I said, when you perform spatial join, not only the geometries merge, but also the attributes merge as well. So here you can see that in the new output data set, there's column information both from the road data set and also from the tracked data set. And this is what our output looks like. So that's all I have for this part. And in the next one, we are going to talk more about spatial overlays and proximity analysis. Thank you.